inviting me. And apologies to everybody, because I actually have to teach during this week. I have double as many of you in Portugal waiting for me, so I can only be here for 1 day. So I'm really sorry. I hate it when speakers just show up for 1 day and leave, but there's no choice, so apologies for everybody. Also, part of what I want to talk about is sort of ongoing work, so any comments you have will, of course, help us move ahead. All right, so Nicola asked me to give a slight introduction to Resurgence, so I'll probably start with an overview of Resurgence applied to string theory. And then I'll give some examples. I'll talk about something which we think is sort of relevant, which is resonance. And then ongoing stuff on the connection to large n-dualities. This is with a lot of people, and ongoing work with my students. And well, Max is no longer a student now, so we'll stop with Max. Okay, so for about at least half an hour, I'll be doing just overview. So for those of you who know anything about Resurgence, I'm sorry, but I'm just fulfilling what I was asked, and I will happily do so. So we're interested in Resurgence, at least I am, within the context of string theory. And so what's the issue here? So the issue is that when we talk about string theory, we usually define it perturbatively, and that's what we have. So I write down a free energy, and it looks as an asymptotic series. Something that looks like that. Where T is some background moduli, and GS is a string couple. And this, of course, is the famous expansion in Riemann surfaces that looks like that, right? Everybody must have seen this at some stage. So what happens is that this is an asymptotic series. So these FG guys here, they go as 2G factorial. This is the famous result of old days. And so you may ask, how can we say anything non-perturbative? This chalk is all wet because I thought of got everything wet trying to make it wet. Non-perturbative. And of course, this is where Resurgence will come into play. So there are sort of two options that you could have here. One is, can I give a non-perturbative definition of string theory? And this I will not talk about. So this would be stuff like ADS-T, string theory, or whatever you want. And the question is, can I instead do something else, which is obtain a non-perturbative construction of string theory starting from such an asymptotic series? Hopefully, yes. So get some information from these guys, and they would tell me something. This chalk is also completely wet. They would tell me something about how to do non-perturbative string theory. So what do we expect to find when we do something like that? We'd expect to find, of course, whatever we have which is perturbative. GS squared, well, let me just say to some specific power. This would be the perturbative guys. And then I expect to find terms, the leading terms are sort of this type in string theory. They go as exponential of minus 1 over GS. These are the leading non-perturbative contributions, and they famously come from either eigenvalue tunneling, as shown long ago by François David, or D-branes, as also shown quite long ago by Polchinski. This should not be the whole story. If you look at it, the perturbative expansion is in powers of GS squared. So the naive expectation that you would have would be that you should have stuff that looks like this. And this would be the so-called NS branes or whatever. This is less obvious how to get from Resurgence, but I will make some comments about it at some stage. Okay? One thing which is sort of prevalent throughout is that, of course, there's some large n-duality at play. So I could have done the expansion here in powers of 1 over n squared. I could have had a Toft coupling here. This is, okay, let me put here large n-duality schematically, which is in purple. And then I would have here powers of 1 over n squared. I would have here powers of e to the minus n. I'll have here power of e to the minus n squared. Okay? So can we at least construct, given a perturbative series, which is asymptotic, can we at least construct all these people in string theory? Well, what would we need to do so? Well, we would need a asymptotic series. So when do we have good control over the asymptotic series? Well, not in a lot of examples, unfortunately. So one thing we could do would be to try to, cannot see anything. One thing we could do would be to try to do flat space. Or, say, group manifolds. And the reason why I'm listing these guys together is because sort of the worldsheet CFT is well under control. So CFT is good. But if we want to go to higher genus, well, it's hard. So if we want to do something which is genus bigger than 2, it's hard. So this guy is not so happy. So other examples we might do, we could even consider worst case scenarios than this one. By the way, I can also put here between brackets if we do either Ramon-Ramon backgrounds or even ADS, well, at least not ADS3. Then we are sort of unhappy on both sides. So the actual thing one can do is not a lot, but it's still some models that will tell us something. So we can look at minimal strings, and we can look, well, which basically are associated to matrix models. We'll talk about that in a minute. And you can look at topological strings. And the reasons why these guys are okay is not because miraculously I can start doing worldsheet CFT on surfaces with genus bigger than 2, but because we have alternative methods of computation. So instead of using CFT, what we can do is we can use string equations, which come from the matrix model. More on that in a minute. We can do topological recursion, of course, because we have a matrix model. And with topological strings, of course, we can do the holomorphic anomaly equation. So these are the sort of tools that allow us to generate data and try to go and do some non-perturbative construction of string theory, starting from an asymptotic series. Okay, so then let's imagine that this was done. And then what can we do? Well, we start again. Let me just repeat it here with F, this series. And then we apply to it the machinery of resurgence. Which at the end of the day, what this is going to imply is that my asymptotic series will become a resurgent Rice series. Okay? So let's schematically see how to do that. And of course, I mean, I'll be not giving a lot of references on the whiteboard talk, is hard to, but let me at least say ecal for this part. All right, then let's talk a little bit on how can I do this construction on a generic asymptotic series. So let me for a second forget about the actual asymptotic series I just wrote for string theory, which is in powers of GS squared. It will be important in, I don't know, half an hour. And let's just consider just a toy example. This is sort of the first round of resurgence. And let's look at this asymptotic series. I'm putting a 0 there to denote its perturbative. And I'm going to use coupling X instead of the string coupling GS. So just to remember that we're doing some sort of toy example to start off with. But I still have an asymptotic series of this type. And now I'm going to assume that these guys grow as G factorial. Okay? Again, not to G factorial. That will be relevant at some stage. Not crash into this chair. So let's start with that simpler example for the moment. So there's usually some bounds on growth, which I will not care much about, but for the sake of completeness, let me just say, the bounds on growth of these guys are usually associated to Gevrey growth, and it could be of different type. And so usually for Gevrey P, which is, we'll only be considering, so let me just immediately say that we will only be considering Gevrey 1, but let me just write down the generic bound. These guys basically grow. M is some positive integer, C, I'm sorry, some positive real, C some positive real as well, G factorial to the power P. Okay? So we're going to be focusing on Gevrey 1. How do I make sense of a Gevrey 1 series? Well, I use the Borel transform. So, no. So I hope, can everybody sit down here? So just that maximize the use of blackboards. Borel transform goes from this formal power series I'm given to basically a convergent power series at the origin. And it assigns, let me just get factors right. This is alpha plus 1, whatever it is, to the Borel transform. S is the Borel plane. This is basically, what I'm doing is basically removing the factorial group. Okay. So things you can check is that this object has a positive radius of convergence, and I can do analytic continuation throughout S in the complex plane. So I'll be interested in looking at S is in the complex plane. However, it's not an entire function. So it has singularities. It better have singularities, otherwise it would be extremely boring. So let me just draw here the Borel plane. And there's going to be singularities. Let me draw here a line with some singularities. And so I can define my Borel transform on this plane, and there are some singularities. So then you ask, okay, fine, great. You sort of got rid of this annoyance, which was the asymptotic growth, but then you computed something else. I would like to know, my free energy or my function phi. So what exactly do I have to do to obtain that? Well, I have to do Borel summation, which is basically a Laplace integral. So I denote with this curly s along some direction theta. Let me just, no, I can actually use that direction already. Theta. And the object, the function I'm looking at, this is exponential I theta times infinity, so I'm integrating along this ray. Let me draw it first in white, and then we worry about the orange. So in white everything looks fine, so I do this integration. Alright, and that looks great. Looks great, except that now if we forget about the white and refocus on the orange, of course, I mean, if it's not on the orange line, I don't really care. I mean, I just do the integral and I'm done. But what is interesting is what happens when you're on the orange line, where you have these singularities. Then that integral actually can't be defined. So what you do is you have to, this is called a Stokes line. It's in orange. Let me write it in orange. It's a line of singularities on the Borel plane. And what you do is you define basically lateral Borel resummations. So slightly to the left and slightly to the right. It's a bit dark because this is also wet. I'm not sure how many shots there are not, but. And then you say, okay, great. Can I relate these two guys? Maybe. I'll come to that in a little bit. What is their relation? But for the moment, let's just assume that, okay, I can do it. Now, there's a definition of what the resurgent function is. Which I will not be too worried about, which is just basically a resurgence function is an object whose Borel transform has endless analytic continuation on the complex plane. So I basically avoid a eventually countable amount of singularities, but I can just always wiggle around and do analytic continuation everywhere. Let's not worry about such a generic definition. Let's worry about, or focus on, let's say, on something slightly more mundane, which is a simple resurgence function. And this one is one which is nicer because at its singularities, let's pick a singularity, for example, that one, and let's call that singularity omega. Then the simple resurgence function is Borel transform close to the singularity, S close to omega, let me write it this way, is something that looks like that. Well, now there's many S's. Let me try to do a slightly more broken S. This is a complex number, and it's basically Stokes data. It's not exactly, but for the sake of this talk, it's fine. Stokes data. Then there is the Borel of what I will call phi omega of S minus omega. For the moment, this is just a holomorphic function near omega. Let me not say anything more about it in 5 seconds. And then the singularity, the nature of this singularity here in white is logarithmic. Plus stuff, which is well behaved. So in the definition of simple resurgence function, I could have also poles. I'm not going to worry about poles, so let's just focus on the case that I have a logarithmic singularity. And the name of resurgence comes, of course, because what I see here is that the omega singularity of phi, I see the resurgence of someone else, right? Resurgence of some other guy whose name is phi omega. And so at the singularities I find more people. And with this definition, let me just, there's too many lines already there, so let me just redraw the Borel plane with its orange singularities. With this definition, I can actually relate the left and the right Borel resummations. Because, let's hope that this blue is now better. Yes. I can look at this resummation to the left, pass it through the singularities, and I get basically a sum over a bunch of Hankel contours. And then I get here S minus. But all those guys, I know if I pick one guy, omega, okay, not the same omega, it doesn't matter. Omega is a generic name. I can see exactly what's going on because I replace this approximation here when I cross the singularity, and when I plug it into the integral, you see that basically I shift basically the S to starting at omega, and then I just look at what happens with the logarithmic branch cut, which kills that to pi I. So it's not too hard to see that, oops, the plus is here. The left resummation is equal to, let me write it like this. Plus a discontinuity, and the discontinuity is basically the sum over all these Hankel contours, okay? Which I can evaluate. And it's just a sum over all of these singularities. Let me call them omega n. Let's assume that they're just discrete, labeled by n. And then what do they have? Well, they have the Stokes data, this sort of S, which is not to be mistaken with the other S, omega n. And what else? I had to shift the integral to omega, so I get an exponential term. And then I'm left with the discontinuity, which gives me the Borel, Laplace of the Borel, which is just the resummation. Let me not include the resummation factor. Okay? And so that tells me what the discontinuity is. And so I've sort of, for at least a quite large class of resurgent functions, I can sort of know everything that's going on. And I mean, so far in all examples we've looked at, and I've already mentioned somewhere that, you know, you could argue that we're looking at a limited class of examples, but there's still infinite different examples in there. They're all that we require are simple resurgent functions, and we're happy with them. So let's, for the moment, stick with it. Then what we've learned is that when we cross the Stokes line, let me just okay, I can be well. So as we started off here with an asymptotic series, and we said, can we make sense of this? And we played this game, and we realized that when I cross the Stokes line, somewhere on the Borel plane, because I'm doing the Borel resummation of that asymptotic series I started off with in different directions on the Borel plane, then, all these guys come into play. So I forgot a lot of people. I better include them. And so if we want to, let's call this the first attempt. It's not good enough, so we try a second attempt. Where we are going to include all these people that I found upon crossing the Stokes line, and of course I should do this for every possible Stokes line that I find. So basically what I have to do is now consider this object. I'll tell you what sigma is in a second. So now I get all these exponentials, and I'm going to be now slightly more precise. So I'm going to consider that all these singularities are at some integer times a being some positive real number, which will be, you know, the de-Broglie tension or the instant on action, whatever you want to call it. And just to simplify our formula, and in this case, I get these exponentials that I had here, which are now exponentials minus NA divided by x. Then what else do I have? I have these guys here, which are asymptotic series in their own. So let me write them as asymptotic series. And these guys look like that. Times x to the g plus beta n. So let me put some nomenclature here. So A, instant on action, or de-Broglie tension, or whatever you want to call it. Then I have this sigma here. This sigma is a transseries parameter. And there are sort of two obvious ways to think about it. One is you can think that this transseries is a solution to some nonlinear first order ODE, so it needs to have one boundary condition. They think of sigma like that. The other way to think about it is to incorporate Stokes phenomena. So if you wait 3 minutes, 4 minutes, I'll show you exactly how Stokes phenomenon occurs, and you see that this is basically the jumping of sigma. If you will, when I was here, for some reason, on the left side, I was happily describing whatever system I'm looking at just with the asymptotic series. And when I crossed, everybody else was turned on, so I need to have some way to take that into account. That can be done with transseries parameter. And I have a beta here. This will not play. This is just for the formula to be right. It's just some characteristic exponent. We're not going to care about this any further. It's just for the formula to be correct. So basically, not everybody starts at g equals 1. And these guys, these FGNs, are most of the time Gevrey one asymptotic series on their own. Not always. There's some very simple pi examples where they're not. I don't know, the Gaussian matrix model. But most of the time they are. So that's our sort of first look at how to construct a resurgent transseries. And as I just said, if this guy was a Stokes line, and if there's this jump, you know, this could be the old jump of Airy, I'm studying the rainbow, right? And Stokes. So what I'm missing is Stokes phenomenon. So how does this go about? So let's write it a la Ekal, which is slightly formalized by introducing basically the Stokes automorphism. So, well, I may have a sign which is not quite right. No, it doesn't matter. I mean, up to signs of plus and minus, this talk will be correct. But don't take all the signs for granted. So one way to formalize this is to write this in this way. Oh, sorry. Where's the... Let me not even put the phi there. One way to write the left and the right resummation is in this way, where this funny object is the Stokes automorphism. And it's basically 1 minus the discontinuity. You could ask, why would I care not keep going with the discontinuity? Well, because it's an automorphism. So it's the exponential of the derivative, and this is where Alien calculus is going to kick in. So that's a slightly nicer object to work with. So let's talk about that. Why this guy? Well, as I just said, because I should be able to write it like that. So this object here, with this funny notation, that's a dot on top. It's a derivative, and it's the alien derivative of Ekal. Which is where basically alien calculus starts. And for the sake, funny enough, I have two white chalks. One messy problem. It's where the alien calculus story starts. It has a formal definition. That's an exponential. It looks like a row. There's a formal definition I will really not care about for the sake of this talk. We can just define it basically as it is. So it's the log of 1 minus the discontinuity. The discontinuity is up there. So this is basically minus the discontinuity, minus the half discontinuity after discontinuity, and so on. And so you see that this object is really sort of following every possibly wiggly line you can do around these singularities that I have here. And that's actually how, if you look in something slightly more rigorous, it's how the Ekal definition of an alien derivative comes about, is as a weighted average of all possible continuations around all possible paths that you can think, avoiding those singularities. And then you'd say, okay, great. So how do I actually compute this derivative? Because this is very formal and abstract. How could I be slightly more precise about the object I have here? That actually is not so hard. So where's the discontinuity? Yes, I have written it up there. Let me get another column. So let me just... I have the discontinuity of phi, which is given by this sum over all singularities. So I can focus just on a specific singularity, and this will be my discontinuity at omega n. Is this sort of object? I'm just looking at one piece. So let me focus on, it could be that guy, which now becomes the purple guy. Okay, so I'm just looking at the purple guy, and if I'm doing that, then that sort of focus also comes to this guy, because I can just write this derivative as a sum over these guys with not underline. All right. I did say, how are we going to compute it? And so far I didn't say anything on how to compute it. So now we go back to our sort of motivating example of why I had a single transseries parameter, when I said that you could think of this object here, this transseries, as the solution to some sort of nonlinear first order ODE that you're given. Okay. Then there's a nice property, which I will not show, but which is the following. It can be shown that alien derivative commutes with the ordinary derivative. And of course, we have a transseries parameter, which this guy also commutes. So if you consider basically the linearization of that first order nonlinearity E, it's going to be an homogeneous first order linearity E. So this guy on phi must be proportional. I'll write the proportionality constant in a second, to this guy. This is not right here. Where is the? To this guy. And the proportionality factor is what I will denote right now, like this. And so you see that under this reasoning, what I've obtained here, it's what's known as bridge equation 1. And that tells me how to compute the alien derivative if I know how to take derivatives of the transseries with respect to transseries parameter, which is pretty easy. The reason why this is called a bridge equation is because it's sort of making a bridge between nasty derivatives and simple derivatives. What's the constant of proportionality, or the factor of proportionality? Is precisely Stokes' coefficients. I think I'm already 5 minutes behind time, so clearly I will not come to everything I wanted. But anyway, you can show that these guys, there's some homogeneity requirements you can make on transseries, so let me not go through those arguments, otherwise I'll never finish. Remember that, where did I write it? I wrote it up there. I'm considering singularities of this form, n times a. So ska of sigma is equal to this. So it's really a monomial in sigmas with simple powers, and we can further show that this guy must be smaller or equal to 1, but not here. And these guys are the famous Stokes coefficients. Those guys are not the same as this, but they're related. Okay? That's why here I put Stokes data, and here I can really put Stokes data. For the purpose of this talk, we can assume that they're the same. There are some tabled relations between both, and you can easily, if you know once, find the others. Okay, so why is this kind of neat? Because now, of course, I can use the bridge equations to evaluate why was the Stokes automorphism given the name Stokes. Because I will, in this case, that I'm assuming that the singularities are proportional to A, and if I'm assuming that A is some positive guy, I basically have two Stokes lines, not the ones I drew there. I have a Stokes lines along 0, and I have another one along pi. So what happens when I try to compute the action of the Stokes automorphism along 0 on my transseries? Well, it's the exponential of the alien derivative. Okay. And the alien derivative is given by the bridge equation, where I'm looking at my direction 0, so I should only take the Stokes coefficient 1, the positive Stokes coefficient. So I can actually write this was acting on phi, as the exponential of S1 dd sigma of phi. So you see what I got. So if I start with phi at sigma, I ended up with phi at sigma plus S1. So in fact, I got the standard jump of Stokes phenomenon. And so classical analysis would stop here, but generically, when you have to deal with nonlinear Stokes phenomenon, you can't stop here. You have to keep going, because there's actually, you see, I only considered one, the positive, quote unquote, of all these possible Stokes coefficients, and I still have to take into consideration and possibly infinite amount of them in the negative direction. And so if you do that, then, well, I write down the definition of the Stokes automorphism. But now, when I use the bridge equation, I have to take into consideration all those guys. So this is actually equal to the exponential of the sum of all possible singularities in the negative direction. So I have all s minus n's to the power sigma n plus 1 ddc. And so, if I want to write down a last formula like I wrote there, all I can write is an object that looks like that. There's some, the flow of the formal vector field is now nonlinear and complicated, and I cannot write the solution generically. I will write in examples later on. But so the Stokes automorphism, the Stokes jump in the negative direction is much more complicated. All right, so that's basically the introduction to Resurgence. So is there, while I erase this blackboard, any question on this so far? Okay. So what we want to do is apply this to string theory. So what exactly can we learn? Let me erase this one as well. So that's the guy I started off with, the asymptotic series, the string theoretic asymptotic series, and I want to do some sort of Resurgent train series extension in order to define to construct, there was a blackboard I erased on definition versus construction, to construct string theory non-perturbatively. So if you play this game, which is in the past unerased two blackboards, what you get is that you have non-perturbatively accounted for terms of this type, minus 1 over gs, or if you think in string theory terms, if you think in matrix model terms, e to the minus n. And you'd say, okay, that's fairly good, but that's not the whole story. Because as I said earlier on, we're still missing these terms. Minus 1 over gs squared, or if you want, e to the minus n squared. So you could say, well, come on, Resurgence is not good enough. You've done all these annoying blackboards for just finding, quote unquote, half of non-perturbative data that you're looking for. So how can we account for these guys? Where can Resurgence see these guys? This is a little bit trickier because they're sort of more hidden than the D-brain singularities. D-brain singularities, I see them immediately on the Borel plane, but if I want to see what we would call the NS-brain singularities, you really have to go to infinity on the Borel plane to find them. So what's going to happen is the following. Is that I look at my Borel transform. Let me go back to my toy example with the function phi. And in 5 minutes I will tell you why I keep talking about this toy example, because string theory has a feature that I haven't put in yet that I will leave to the end. An added feature. And the existence of this type of terms in orange if these guys are there, if these guys exist, then everything goes as before, except the Borel transform is no longer, is not, exponentially bounded at infinity. So you see, this is another obstruction to doing Borel resummation. So the first obstruction we found for Borel resummation is the one up there on that picture, which is singularities. I cannot do the integration over the ray because I have singularities. But now there's another obstruction, which is, well, I can actually not do the integration even if there's no singularities because it's not exponentially bounded at infinity. All right, so how can we deal with that? Well, then we need to do basically another trick, which is still in the full resurgence theory of Fekal. So, I mean, in fact, with resurgence, you can do e to the minus n squared, minus n cubed, and minus n fourth, whatever you want. But, you know, as far as we know in string theory, we stop at e to the minus n squared. So what you need to do is sort of, I will call this guy a sort of a second. Yeah, okay. Let's just try to keep notation to the minimum. Second Borel transform is not a Borel transform, but I will use the notation with the 2 over there. Let me put the 2 in another color so it highlights that I'm doing something different. And this object is defined in this way. Of course, I'm not saying what k is. Okay, I can write what k is. Okay. Where this guy is called, so-called, is orange again, acceleration kernel. The role of this object is just to ensure, to remove the growth of the initial Borel transform at infinity and give it good exponential behavior at infinity such that then I can do a Borel resummation, okay? So, yes, let me give you the answer straight off, and then I'll tell you what the acceleration kernel is in a minute. So this guy cures the problems, and then the resummation, which was there when all I had was singularities and nothing else. The resummation is now, so you can compare both blackboards. If I could see anything. Again, same direction, theta. Now it's not on the S plane, it's on the psi plane. And who I'm integrating is this Borel 2. So it's the psi plane, the psi, which comes from that guy. I still haven't said, so I realize I haven't said it all. But give me a second. So you see, the accelerated resummation looks very much like the non-accelerated resummation, but with a different object. And this different object takes into account the following. So now let me say something about the kernel. That there are what in resurgence is known as different critical times. So I have sort of the n, let me do it with n. So let me focus on this case. So on the sort of the matrix model side, which probably is familiar to more people. So I have sort of the critical time n, which I can call the slow time, because I have also the critical time at play n squared, which is the so-called fast time, and hence the name acceleration. I'm moving from slow variables to fast variables. And what's going to happen, basically, is that this kernel, let me now write it here, will look something like that. Assuming that normalization is correct and so on, but this is Z2 is n squared, or is going to be identified with n squared, and Z1 with n. Okay? And so you see something interesting is happening here, which is that the accelerated Borel transform, let's back up a second. The standard Borel transform, the resummation of the standard Borel transform would jump at the singularities of the Borel transform. That's what I sort of try to describe here. Now, it's going to be the accelerated Borel transform that's going to jump at those singularities. So, sorry, I didn't want. This guy jumps at the singularities of Borel. And the resummation jumps at the singularities of this guy. Resummation so now I have sort of two discontinuities to take into account. Jumps at singularities of B2. And so one can ask if one can find okay, I have a clean blackboard. I think I reversed the order of the blackboard. It's fine. Can one find the NS effects? Maybe. So that's ongoing. So in some examples, we know for sure that they're not there, which is interesting. So that they only have D-brane effects. There is no NS-brane. And there are other examples that, well, the computer is trying to check. You see, we only have numerics on these guys. We don't have analytics. So to actually prove integrability or not, it requires a lot of data. Maybe. Well, let me put it this way: if you want to find them using Resurgence, this is what you're going to have to do. So maybe you can't find them using Resurgence, but well, we don't know. So you could say, okay, fine. Now I have my perturbative series, which was asymptotic, but then I found my D-branes, or my eigenvalue tunneling, and I was sort of so happy, not so much because I knew from string theory that I should have more guys, but I found more guys, at least a way to maybe find them, and then say, okay, now we're done. Have we finally constructed non-perturbative string theory? Not yet. So there is one more thing. In fact, the reason why I still keep that guy up there, but let me just rewrite it here so that we don't jump around blackboards all the time. This is a power series expansion in GS squared. Or if you want, in 1 over n squared. I mean, it doesn't really matter which way you rather think in terms of string theory or matrix models. It's up to, whatever is your preference, and basically you have the same information. And because this is an expansion in even powers, what this implies is that the Borel transform, which has already been erased, but well, you can recall that it was just removing, there was a formula just removing the factorial growth, has fixed parity. So the Borel singularities are actually symmetrically distributed on the Borel plane. And what this means, effectively, is that the string theoretic expansion is resonant. But I think I'll only talk about this on the second lecture. So, okay, maybe now we're happy. That's pretty much it. Not yet. Because you could say, well, what about other observables? Or I mean, you've been talking for almost 1 hour, and all you've managed to do is to convey the idea that maybe you've managed to construct the string theoretic free energy, but that's just one out of a lot of observables that I would care about. So, for example, other observables. For example, de Bruijn amplitudes. This would be sort of the, I would say, canonical example, at least to me. I mean, canonical might not be a very objective word. What can I do with these guys? Well, the first thing you can ask is, what kind of de Bruijns do we have in our models? So what's the de Bruijn spectrum? And this is basically ZZ brains, which can think of as instantons, which is all that basically I've been talking about so far. All those singularities are sort of the ZZ guys. And then there are the FZZTs, which you can think of them as basically as D0 particles. And let me say a word then about these guys, this class of observables that we haven't considered so far. So in the matrix model, you can think of these guys basically as waveforms. Let me write it in a way that I think should be familiar to everybody in the audience. For n by n random matrices M with potential V, you have to compute the correlator of a determinant insertion. I'll be interested in the double scaling limit. So, in double scaling limit. All right. So, what can researchers say about these guys? Well, it turns out that they satisfy a Schrödinger-like equation. So, let kappa be double scaling limit of G string. Okay, and let me not be more precise than this. Then these guys satisfy an equation that looks like that. And you'd say, that's a Schrödinger equation, but that's actually, ironically, which is sort of the more intricate part of resurgence, is probably also the best well known because of all the applications in quantum mechanics. But, and you'd say, okay, fine, but that's, well, crossing, DDP formula, and so on. I'll say 2 more words about it in a second, except not quite, because this guy is not a polynomial potential. This guy is a solution to the string equation. So this guy is a trans series in itself. So this has added issues for what I have to say. Say 5 minutes? Yes, I can still finish this. Okay, so any questions while I erase more blackboards? Erase them all. Okay. So the analysis, the resurgent analysis at least, is now different. Resurgence. So what we've been doing so far is what is known in the resurgence world as equational resurgence. But the analysis of Schrödinger type equations is what's known in the resurgence world as coequational resurgence. And the distinction is basically that in equational, I'm basically doing formal series in the variable of the equation, of an equation. For example, when I was talking about the trans series being the solution to some nonlinear ODE, actually in the blackboards I just erased, you could think that that was an equational case because I was doing resurgence, asymptotic expansions in the perimeter of the equation. And coequational is what is not in the variable of the equation, so it's not in kappa, but it's in, okay, h bar. Maybe I can put an h bar there. And a calculus is the inert variable. And now, I think I have 2 minutes, so let me be a bit schematic to try to just wrap up all this overview part. So what we have in equational resurgence, we had what I called at the time bridge equation 1, which was basically this object. Let me just write it like that. But if I want to do now coequational, I get two new bridge equations, very schematic. I get the so-called bridge equation 2, which is of the same type as bridge equation 1. Let me put a different S here. This actually, I should put this E basically, because this is, at the end of the day, is going to be a Voro symbol, but anyway. Which can now depend on H bar. This is schematic, so let me put quotation marks. And if you know WKB, this is what happens when I cross the Stokes line with my wave function. And then there's bridge equation 3, which in resurgence language is kind of nonsense. In fact, I'm going to be even more schematic. Because Stokes data now is H bar dependent, it actually can, and in many places is, an asymptotic series in itself, which means it will satisfy a bridge equation of its own. And so there's bridge equations of this type. Again, this should be a V, but okay, whatever. And this is, here's the interesting part. That's why I'm writing these bridge equations, which are not very enlightening most of the time. This is a function of the S's alone. Maybe I should have put an omega there. Maybe I should put another omega there. And let me put omega prime. So that's the point, is that bridge equation 3 actually closes. So whereas bridge equation 1 requires Stokes data, and it can be sort of hard to find it, and bridge equation 2 as well, less hard to find it because, well, in a WKB, yeah, okay. In a generic, maybe equally hard to find it. But bridge equation 3 doesn't need anybody new. So it plays with itself, and everybody's happy. And of course, the simplest way to actually see this is by writing the DDP formula. Okay, can I have 2 more minutes just to finish the... I'd like to finish 2 pages, is that too much?
Well, these are 2 minutes?
3 minutes?
Let's not talk in terms of pages, let's not talk in terms of minutes. Okay, 2 minutes.
Okay.
You have an hour. You have an hour later. Don't worry.
No, but I have more pages than.
Yeah, but the important thing is that people follow. Not that we don't have to take an exam after this. So
You think, but I have something here. A surprise. Okay. So DDP formula, just to tell you that this encloses for Voro symbols. Looks something like that. So this is quite clear. I mean, if you've never seen WKD, let's not worry too much about this. If you've seen this formula, and it's quite clear how basically I live happily with this and nothing else. And then you could say, okay, then we're done. In fact, recent work by Marcus has shown that this DDP formula is actually quite generic, also in many examples in topological string theory. And you'd say, okay, so I'm done. I finished, these deep brain observables are simpler. Well, not exactly. Because there's still an issue, which is that there's extra singularities, there are extra Borel singularities associated to the fact that the potential is a trans series. It's a solution to the string equation. So there are added, for S as a T, there are added Borel singularities from this being a solution to the string equation. And I'll write down a solution to the string equation in the second half of the lecture. Okay? So there will be some extension of TDP for that, which one of my students is looking at. So anyway, that's the resurgent analysis. And you say, okay, great. So now we've done all this big tour de force and we've constructed non-perturbative free energies and maybe non-perturbative de-Brane amplitudes. Once I get to a hold of all these singularities, not only the, let's call them classically WKB singularities, what can we apply these to? So application. So of course, there maybe, I mean, again, you know, like canonical, the word application is not objective, so I mean, maybe my favorite, and you find it uninteresting, but you find other things interesting. But so one interesting thing that for me is large N duality. Can you learn anything about large N duality between, you know, basically, if you will, open strings, which for us is going to be matrix models, and closed strings. Which for us is going to be basically topological strings. So usually, let me just try to finish everything in this little piece of the blackboard. So usually, people try to show or understand large N duality on the world sheet, right? So you look at open strings, you look at world sheet with boundaries, and you try to map these to world sheets without boundaries. And in the matrix model context, there's been actually recent progress. But we're sort of thinking slightly different. And this would be, let's say, world sheet. We're thinking target space. So if I have something that came from matrix models, and which was computed, you know, via string equations, or via the topological recursion. And as explained throughout, I construct a resurgent trans series solution to that problem. Can I show that that solution is the same as the one that I would get from topological strings, which I would have computed using the holomorphic anomaly equations? And so this is very much in the spirit of Dijkgraaf-Waffe, but in a different phase from what Dijkgraaf-Waffe is about. And I think my 3 minutes are up, so I'll explain what I mean by this in the second lecture. Thank you. Question?
I have one. So you explained that when you have NS-Brane effects, the Borel transform will not be exponentially bounded with infinity. And then one way to define the Borel sum is via this acceleration term of distance, right?
Yes.
Is there some intuition of why that's the right thing to do? Because there might be a lot of ways to fix this.
Well, yes, but I mean, that's the same as saying that there will be many ways to fix the asymptotic growth to start off with. I mean, why do I pick the Borel transform and nothing else? This is just the thing.
There's an argument in that case that perhaps would justify what it.
The argument that I would use for that case would be the same argument that I use for your question, which is the one that gives the most interesting structure.
Okay.
and which in fact can then, I'm only talking about NS, but you could have any amount, you can have an infinite amount of different critical times. And all that works neatly and very nicely with all this acceleration and acceleration kernels. And so I think that there's a very interesting structure there. Maybe there's a deeper explanation, but I'm quite pragmatic that this is working fine and I'm happy.
Okay, let's thank Ricardo again, and then, let's...
Okay, thanks. So let's do some examples. So there's, of course, many examples that one can do with, matrix models. And double scaling limit of these guys, so multi-critical models. And so on. So I'll just be focusing on, and of course I'll be equally schematic, but I'll be focusing on these guys just for the sake of writing smaller expressions, but whatever I'll be saying holds for everybody. So let me just tell you something briefly about multi-critical models. And these guys basically have, here's the spectral curve of these guys. Zeta now is the uniformization parameter of the spectral curve, not the zeta that was before in the acceleration kernel. And y is given by this. So I forgot to say something. All these guys are going to be, I'm going to be focusing on the when matrix model. So they're labeled by an integer k, as in the usual 2 to k minus 1 multi-critical models, minimal strings, which appears here. And then there's a polynomial. It's a hypergeometric polynomial. There. And if you do, this is sort of the natural construction that appears from the matrix model side. The natural construction, because this of course is an old story of how open-closed duality goes for these systems. The natural construction that appears from, say, the CFT or closed string side is slightly different. It's the Chebyshev polynomials, of course, where x is the same, but now y is 2k minus 1 of zeta. So instead of having a hypergeometric polynomial, I have the Chebyshev polynomial. And so there's an old story that I'm probably, just to make sure that I actually finish all my notes, I will jump two things. And this is one of the things I'll jump, which is that there's an old formulation of open-closed duality, right? Where you'd have, I don't know, the triangulation of surfaces. And so you would have a map between the matrix model and central. Right? So this is just to say, if you don't know what the story is, it doesn't matter. It's just to say that there is some old-fashioned approach to looking at open-closed duality in this context. And another way to basically do the same is sort of a perhaps more modern approach, is to compare these sort of correlators in the matrix model side with the thermal partition function on the bulk spacetime, and this also gives you another way to do these things. Okay, so this is just two comments, and I'll jump this so that we can come to the end. So let me just write it in words. There is a quote-unquote classical approach to open-closed duality. In these examples, And now what we would say would be that this is in the Stokes phase. And I'll come to that at the end. Okay, so I just jumped that, but it's there. That's the sentence of what I could have done in a page. All right, these things, of course, are not completely independent, and it's an interesting thing that let me just put it here in quotation marks, and then I'll write the formula in a second. Is that minimal string spectral curve is basically given by a sum over KdV times of the multicritical spectral curve, right? And what we'll see is that whereas from open-closed duality, sort of the minimal string may be the most interesting object to work with from the point of view of the matrix model, it's the multicritical string, or multicritical model, whatever you want to call it, multicritical theory, which has the building blocks to construct the string equations that we can then use. And this, by the way, are building blocks that can be used to describe things in a different class from just multicritical and minimal strings, as again, I'll try to come up in the end. So what are these building blocks and how do we do computations? So the way we do computations is using string equations. I mean, computations, of course, in the spirit of what I taught in the previous hour, of we want to construct Resurgence train series solutions to some problem. So what is the problem? And the problem are string equations. So in the double scaling limit, which is basically where everything lives that I'm going to talk about, is of course are given by the Gelfand-Dickey KdV potentials. So let me just write down the recursion, and I'll write maybe one example. But although I'm just writing one example, let me emphasize that everything that I'll be saying pretty much seems to work for any example and any quote-unquote linear combination of examples. So by these sort of relations. And the example, of course, is R2, which is this guy. Okay, and U, let me just be more specific here. So R is the KdV potential. U is what we will call the specific heat. And it's the object for which the string equation is written. So the generic form of the string equation for multicritical models if I consider the 2k minus 1 multicritical model, then the equation that the specific heat of that system satisfies is this one. There's basically, this is some normalization. I could have done it, but let me write the correct formula just for the sake of it. And then there's the RK Gelfand-Dickey KdV polynomial on U equal to Z. All right, but Z, that's U is a function of Z. The specific heat U is a function of Z. So if I just consider the 2,3 case, this, of course, gives you the Pauli equation. Pauli 1. You can consider 2,5, and then you would have, let me just write down the beginning and the end of the equation. Minus stuff plus 1 over 10 U. And so on. So what you would like to do would be to solve all these string equations in the KdV hierarchy and in the minimal string hierarchy. We're using this Resurgence train series and try to see if you can then use the technology that we just discussed and start producing solutions which may have D branes, may have NS5 branes, may have SSAT wave functions, so on and so forth. So this is the multi-critical case. And now let me just say, how would you do the minimal string case? Just to tell you that there's minimal string. Solving these equations, I should have put in the box there because there's another equation. Well, there is. Solving these equations is not enough if you want to basically solve all possible problems you may have. So where was it? This equation here, the curve of the minimal string, which is this Chebyshev polynomial, can be written as a sum. Well, I'm just putting in slightly more words, or more formula, should I say, what I wrote above in words, where this guy is multi-critical. So the Chebyshevs basically are a sum of specific coefficients of the hypergeometric polynomials. Let me not write the formula for t. It exists. This is just to say that then we can write down the minimal string equations by using these guys and this sum, precisely by using that relation. So that the minimal string equation would be, for generic case, would be precisely this. So you see that I would also like to solve these equations. Okay, let me, there's all this normalization factor. But just to say that you can also write down other equations. Just to give you an example, which is just a stupid example, if you do the 2,3, you obtain this equation, which up to normalization is again polynomial 1. So this is not, the first example is not terribly interesting because it gives you nothing new, but already when you go to 2,5, and instead of starting, so again I'm just giving you the first and the last, so now you start with, well, there's a normalization factor, and you start with minus u. So that's already a new string equation, and so you have these large classes of string equations that you would want to solve. So how would you come about and do it? Well, we just play the game that we talked about in the past hour, and so I will ask for a resurgent trend series solution to those infinite classes of string equations. And you say, well, let me write down an ansatz based on what we discussed earlier that looks like that. And you immediately know, wait, do I have two white chunks? You immediately know that what I'm saying has got to be incomplete because we already discussed this last time, which is that the trend series parameters are sort of like boundary conditions for these nonlinear ODEs. So if I am having an order 2k minus 2 ODE with each k, of course one parameter is not enough, but for the sake of the argument, let's just push it a little bit further to see where we arrive at. You have something like that schematically, and so this is of course not enough. The problem is that I need more sigmas, which implies that I will need more instant actions because I have a 2k minus 2 ODE coming from all these problems here, multi-critical or minimal string alike. So in fact, you can show by just plugging in these ansatz that the instant on action. Okay, well, I can write the formula. If I normalize it in this way, then this is given the rho is the root of a degree k minus 1 polynomial in rho squared. Okay, so this is the story, if you want, that we already discussed when there was a previous blackboard here, I don't know which was one of these ones, when I said that the Borel transforms of string theory had this symmetry on the displacement of singularities, and now we see this exactly, because this is a root of the Greek k minus 1 polynomial in rho squared, then the instanton actions are actually a vector of this type. So you have all these pairs. This was first observed by Polynomial 1, by Marcus, but this is actually quite generic for anybody here in the multicritical or minimal similarity. In fact, for anybody on multi-matrix models. So, which, I'm not writing here, but if you want, there's also string equations, of course, for generic matrix models, only they're finite difference equations instead of being ODEs, but so let's not get into that. But anyways, so things work just like here, and it's fine. So,
Ricardo,
is that?
just a question.
Yeah.
So the string equations or the primes that you're writing, are these derivatives with respect to
Z. So U is a function of Z. So the primes are derivatives with respect to Z.
But it's
Z, then
Resurgent and GS, right? So
yes, so that's what I was doing. And you can relate Z, so I'm sort of hiding a little bit of things. So, okay, let me include this just for the sake of being rigorous. So in here, Z relates to GS to some power. I forget what the power is, it doesn't matter. So then you can make that relation. And that's the story that goes on in the multicritical case. In the minimal string, actually GS appears explicitly in the equation, and you solve things in Z, and then you have to take Z, well, let me be more rigorous. You have to take U0, which is the genus 0 free energy, to 1 at the end of the calculation, which in many cases sets Z to 0 or to 1. It depends on whether it's even or odd. And this is what Seibert and Schick call the conformal background. So at the end of the day, all you're going to get is power series expansion in GS. So Z still needs to be set to the conformal background. But I didn't want to get into technicalities. Z still has to be set to the conformal background. And so everything is just going to be numbers, a symptotic series in GS with number coefficients.
and the specific heat is the analog of the partition function. So this is
the CZ heat, F2 prime is equal to minus U, and Z is exponential of F. Okay, so just sorry about that. Is that clear? I should have said it. I apologize. All right. So what we're expecting is not only that we get a resurgent trend series, but that we get the resonant resurgent trend series. All right. So let me give you a schematic example of what the resonant trend series would look like for Comet V1. And it would be something that would look like that. U of GS, now it's going to depend on sigma 1 and sigma 2. There's going to be two sums. There's sigma 1 to the n, sigma 2 to the m. Then there's going to be exponential of minus m a over GS. And then there's going to be a symptotic series. Let me not worry about them. Asymptotic series. We don't need to focus on these anymore. I don't have a lot more to say about these guys than what I already said in the first hour. What I really want to talk about is the fact that here you have n minus m, which means that at the non-perturbative level, you can have contributions to the trend series which do not have an exponential transmonomial. So, what's that all about? Okay, so now we change to part 3, and let's talk a little bit, resonance and resurgence. All right, so the idea somehow of what resonance is from a resurgent point of view is sort of the following. Let me make sort of a drawing. You can think of this this two-parameter train series is labeled by two integers and an m, so you can think of the train series as sort of a semi-positive lattice, where at each node, let me not do a plot that would take 5 minutes to draw, but at each node you have some sector n, m. And then of course you populate them 0, 0, 0, 1, 1, 0, and so on. And it so happens that the way you move from the train series lattice, so the train series you can think of it as a lattice in Z 2k minus 2. Let's not just think about only V1, but let's think about any of those guys that we have here. And this projects, this is sort of the train series, and it projects to the Borel plane. You see, basically if you have a site, it's L dot A. So this, if you want, is the projection that takes me from train series nodes to possible resurgent singularities on the Borel plane. Because remember that if I sit at any of these nodes, resurgence allows me to see some other node. So I'm sort of labeling, possible singularities. Not necessarily there's a resurgent link in between, I don't know, 15, 17 and 21, 23, but then that just means that the Stokes coefficient in between those two guys is 0, but in principle there could be, so I'm just allowing for everybody. And so the idea of resonance is that if I have this projection, I can have a projection that looks sort of like this. Let me see if I can illustrate the plot, versus a projection that looks like that. So this is, of course, non-resonant. The kernel of the projection is basically 0, because everybody goes to a different spot. And this is non-resonant. And this guy is resonant, where a lot of guys go to the same spot. And so you immediately see that something special is occurring. I mean, now you just rotate this guy. It's occurring along the diagonals of the train series. And one diagonal, of course, is the main diagonal, where this guy in the main diagonal is equal to 1. So there's an exponential, non-perturbative term that suddenly looks perturbed. So that's the idea. So let me now just do a couple of calculations on the Borel plane. I'm sorry, on the bridge equation. So here's the bridge equation schematically. If I have my two-dimensional case, so now singularities are at L dot A. Those are these singularities here. Of my nth sector, I'm putting a vector, but I'm just meaning nm over there. And this is going to have a Stokes coefficient dot n plus L n plus. So this is what you may recall. It's written in the so-called non-pointed version, but that's just the technicality that we don't care. It's just the bridge equation, slightly rewritten, the bridge equation 1. So the alien derivative of phi gives me another phi. And so I can compute them all in this way. So what would Stokes data now are vectors on lattice sites. So 2D vectors on 2D lattice. So let me try to write down how do they look like. So this would be sort of my lattice. These are my axes. Let me just get them straight. And so I have guys basically here, 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 and I have other guys. See if I hope I'm not putting this wrong. Here, 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 and so on. And so there's basically, they're almost all in the third quadrant. I'm being descriptive. So, I mean, you can show all this, just telling you the story of how it goes. And you have these blue guys the ones that sit here, let's say there's a diagonal that has nobody. Let me just... So there are the guys below that diagonal, we sometimes call them forward Stokes vectors, and the guys above diagonal, we call them backward. And if you know one set, you know the other. So we'll focus on the blue set, and that's it. And they have, okay, let me not give all details because anyways I'm being descriptive. So they have an interesting vectorial form, which looks like this. So you can immediately see that they're very much aligned along diagonals as I write this. So this is the lattice site, 1 minus p, 1 minus p minus l. And this is given by a number. These are the things we're going to focus on. Times a 2D vector, which is very easy to write. And so everything is about, if you want to know Stokes data for one such problem, and of course, if we're talking about the two-dimensional problem is polynomial 1, but we could do this for anybody else. We're really looking for those numbers there in those purple boxes. So let me just say that P is a semi-positive and L is a positive integer. And so you see that these guys are sort of aligned along diagonals. And so you can ask, can I find Stokes data? So here would be a Stokes vector. Stokes data. Let me put between brackets, this is for polynomial 1, because I will write an explicit formula. But in principle, you could do this for other things. So where is it? We're finishing this 2,5 example, which seems to have enough information to basically dictate Stokes data for all members of the KDB hierarchy. So Stokes data, Stokes for polynomial 1. Well, I guess I should have said after Stokes data for polynomial 1, but okay, let me not erase that. And these objects look like that. So you can sort of find the boundary is sort of easy. By the boundary, I mean this outer boundary here. So these guys are easy. They have this simple expression. L just tells you which site you are. So it's telling you the starting site of the purple diagonal in white. This number, N11, is the famous number that's been computed by a lot of people. So in the matrix model context by François David. And then I can find out what's going on along the full diagonal. Let me say one diagonal, but I've already formula for generic, which are of this form. I introduce a generating function, which depends on lambda, which is just basically the starting guy, if you will, in white, and then times 1 over gamma function. And well, I can write down. There's a number, this again is for polynomial 1, so these numbers are the ones that come from polynomial 1. And then, if you want to know the specific numbers, you just take the derivatives, right? So that's what you wanted to do. So maybe this is a little bit too technical, but okay, to write down at least one formula. And you say, okay, that's a bloody mess, but okay, I found all those numbers. Great. But this is ultra complicated.
Sorry, excuse me. So what is lambda?
Lambda is just a generating parameter. So this I'm setting up a generating function, and the actual numbers are
I see.
derivatives of the generating function. Is that clear? And then you would say, well, this is ultra technical and I'm getting bored, so why is this of any relevance? Well, why did you even write that for me? Well, because the diagonals are important. And so you can ask, what's going on exactly along the diagonal? Well, it so turns out that if I'm going to look at this Stokes coefficient, I don't want to say anything too technical, so let me just write down systematically. Yes, blackboard. So, any other questions while I raise one blackboard? it turns out that that looks really nasty. 1 over gamma function is going to give you, zeta numbers, so it's going to give you transcendental information. But is it that? And by the way, so this is for polynomial 1. As you go to, the Yang equation or higher members in the KDV hierarchy, this is again the same structure you're going to find. You find 1 over gamma functions times higher dimensional vectors, which organize again in pairs. And so you have a lot of, let's say, zeta transcendentality going around, and you'd be feeling, you could feel like saying, well, that's a bit boring, you're going too technical, please change subject. But let me just say that this can actually be of interest because you can repackage all this information in a much simpler way. So let me try not to give too many. Okay, my glasses are now white. Let me not give too much information. Let me just say that Stokes data organizes in the following way. So you can actually write down expressions for the full Stokes vector. So when I underline and put a 0, I'm just saying that I'm choosing the 0 direction, or I could choose the pi direction. This is the resonant Stokes vector that includes all these little Stokes guys associated to each lattice site. And if you do so, this is I promise, the last nasty formula I write. It looks like this. This is an n. This is me. So let me just write it all, and then I'll say what the different things are. So I'm sorry for this, but it's not because I like to write nasty formula or be in any way very precise if I'm giving a Blackboard talk, but it's just to convey that there's really a huge simplicity occurring here. So let's see, N11 is the guy on, which is the easy guy. Did I write it somewhere else?
Yes, next to it.
Ah, yeah. Then I have, so it appears there and there. Then I have this function. This is the same function. There it only involves the 1, but it doesn't matter. It's the same function. Where you could say that there lambda, as Kohei asked, was just a generating parameter, and here I have something which depends on sigma 1 and sigma 2. By the way, there's a sigma 2 there. There's 1 over sigma 2 there. There's sigma 2. Where is sigma 1? Well, mu is sigma 1 times sigma 2. And so this includes all Stokes data. And you say, well, that's absolutely horrendous. Yes. Now here's what's not horrendous, is that if I start with this guy, and I take the inner product with dd sigma, if you want the right-hand side of the bridge equation, then I'm changing from variables sigma 1, sigma 2 to variables mu rho 0, which, if you want, are the variables, I can use this lattice, are the variables that are parameterizing in orange what we can call the diagonals of the trans series, and so we can call this a diagonal framing of the trans series to compare with what would be the white part, which would be the rectangular framing. And this becomes basically, let me call this guy P naught rho 0 times dd nu. So in diagonal framing, this is horizontal. It's an horizontal vector field, and in particular, or maybe I should have said what rho 0 is. Rho 0 is just this function. So I move from sigma 1, sigma 2 to mu rho 0, which means that the Stokes transition which, let me recall, in the polynomial one case, in rectangular framing, is really a mess because it involves all these zeta numbers. And it's going to be highly nonlinear, and you have to do this nasty integration of these vector field flows in these new variables is just a shift, and it's literally a shift because this is at theta equals 0. Rho 0 doesn't jump. There's also another one at theta equals pi, but let me not write it because the story is the similar. And so you see that the alien vector field is really very simple in this framing, and there seems to be something special about grabbing this trans series. And again, this is generic. This is for any trans series you may want. Was there a blackboard? Oh, it's already erased. So it was a formula that was in that blackboard. For any trans series you may want of this multicritical series or of this minimal string series, you have all these resonant guys, which means that you're going to have much simpler alien calculus if you consider what's going on along diagonals than if you consider what's going on rectangularly. And as I hope to explain, this is not just a curiosity, this is also associated to some sort of way to think about large hand duality if you're outside of the Stokes phase, which I hope to come at the end. I have 20 minutes, right? Yes. Yeah, I think it should be okay. I'll just jump one more second to that. I mean, I think I went over time on the previous one, so I'll make sure that I don't go over time on this. I will do slightly less time. Yes.
So P0 is what?
It's this function here.
Yeah, but
It's basically a log.
Yeah, but how does rho 0 appear there? I mean, when you say it's a function of rho 0?
So here was a function, yes, because rho 0 is sigma 2 times n11. So let me give you the correct formula.
Okay. No, that's fine.
Sorry?
I can see.
So if I want to be more precise, I'm going to write here P naught of sigma 2 times n1, which is the combination that's appearing there. Right? And then what I'm doing here is I'm just using rho 0 defined as it is below. Is this clear?
Yeah.
Sorry, I'm trying not to give too many technical details, but then maybe I fail on some definitions. Sorry about that. So what would be the generic story? So what's the 2k minus 2 story? Is this the same? So let me not try to write down most of it. Let me just try to write down some analogies. Let's see in green. What's the analog to this quantity in the 2k minus 2 case? Well, it's something that's going to look like this. Sigma 1 n1, sigma 2 n2, sigma 2k minus 3, and 2k minus 3, sigma 2k minus 2, and 2k minus 2, and then the exponential of minus 1 over gs, n1 minus n2, a1, and 2k minus 3 minus n2k minus 2 times ak minus 1. And you see that what we had up here, which was the fact that there are diagonal directions along which the transmonomials go away. Now there's a lot of them, right? Where they partially go away, and there is one main diagonal where everybody goes away. So you're inclined to introduce diagonal variables for the generic problem, which are of this type. U1 is sigma 1, sigma 2, until uk minus 1, sigma 2k minus 3, sigma 2k minus 2. Okay, so this is basically the resurgent analysis of what resonance implies, is that when you have your trans series, there is a sort of a seemingly so far, just technical way to rewrite stuff in a more compact, neat way. Now, is there anything else to this, or is it just some interesting technicality? Let me go to section 4, and I will basically say nothing here, which is physical resurgence. Not resurgence, resonance. Sorry. So I sort of tried to motivate that technically, at least, it looks like this is a feature. Well, it definitely looks like it's a feature. And maybe it's of some interest in rewriting solutions. They certainly look like things are better reorganized. Stokes data becomes quite compact to encode. Stokes transitions become super simple. So is there any physical reason why this is the case? So let me just say 2 words about it. Not on the matrix model side, there is a reason for resonance, which is the existence of what we call anti-eigenvalues. And I'll make a picture about that in a second. But there's also another explanation from the conformal field theory point of view, or maybe I should say from the boundary conformal field theory point of view. And it's the analog of anti-eigenvalues, which are negative tension difference. Okay, so let me not give technicalities and just make 2 or 3 pictures. So from the matrix model point of view, what's going on is that if I consider my spectral curve, and let's consider a genus 1 spectral curve which has been pinched. So I have a cut, A to B, and I have a pinching, which is usually associated to a non-perturbative saddle. And what we usually do is we consider eigenvalue tunneling to describe the instanton effects in the matrix model, right? And so what we have to do to incorporate resonance, and in fact to predict all the trans-series sectors out of matrix integral computations, is to consider basically eigenvalue tunneling on the involuted sheet, which on the physical sheet behaves as anti-eigenvalues. So it's basically, it's like reversing the charge of your eigenvalues. And let me not... okay, let me say one thing, maybe just one tiny technicality, not to do any computations, is that when you compute matrix integrals for trans-series sites, so if I compute curly Z would be the matrix integral partition function on the 1, 1 side, and we usually normalize these guys by the perturbative, and this is going to be an integral. Let me not put coefficient or anything. So there's an integral over an eigenvalue that I've tunneled, say in blue. Maybe I could write it in blue. And an integral over an anti-eigenvalue that I've tunneled, which is the yellow guy. And if I do this, there's going to be something here that I need to evaluate from the point of view of the integral, which is basically a correlator of determinant insertions. If you've seen them, fine. If you didn't see them, it doesn't really matter. And the novelty is that what I get here is a pole. So when I'm doing contour deformations, which is how I usually evaluate this saddle point integrations in matrix models. Now that is not enough, and I have to include residue contributions. And if you do so, you can do matrix integral computations and basically reproduce the whole sectors that all those asymptotic series, if you will, for your resurgent transseries. Let's just keep it at that. No more technical details. And let me just say that from the point of view of boundary conformal field theory, what you do basically, okay, maybe I should say even less details here, but you do an integration over FZZT moduli space to compute these very same contributions. And what's going to happen, I'm going to be ultra schematic as well, is that you're going to have, it's the same picture, but now you have the FZZT moduli space, and you have sort of the two sheets of the moduli space, and the integrals you do of this type. Maybe I shouldn't use the same Z because this is now not the matrix integral, but let me put a hat on it. No, I'll put CFT on it. BCFT. BCFT perturbative. And this is going to be, well, integral over moduli space of the exponential of basically distances of disks, of FZZT disks, that basically are going to give you the ZZ non-perturbative contribution. It's a bit schematic, but let's leave it at that. And these differences at analyst level give you exactly, so when you do the computation, these guys produce the same poles, and so the integration over FZZT moduli space ends up giving the exact same integrals as you find from the matrix integral side, because of the inclusion of the negative tension branch. Okay, so I think I wanted to finish early, but I'm going to finish on time. So let me just give you any questions while I raise the last blackboard, and then I'll try to wrap up with some generic remarks on large N duality. So there's more details, of course, to this section 4, but okay, let's just keep on those two very schematic formula. So any questions on that while I erase this? All right, so last point. Resonance and large N duality. So now we have this trans series, and you can ask, well, what are the implications of these things? We know that the trans series are resonant. We know that they're resonant because you either have to consider both eigenvalue and anti-eigenvalue tunneling, or you have to consider both D-branes and negative tension D-branes. Does this have any further physical consequences? Well, let's write down the free energy of, say, a 2-parameter example. We can think about this as being Polyville. And now, I'm afraid did I erase both blackboards? Yes. So I'm going to consider, okay, I can write it down again. I'm going to look at this in this diagonal framing, where I've used this apparent technicality to see if I can gain anything from a more physical point of view. And so if I do so, what I'm going to get is the following, and I'm just, here it's just rewriting of the trans series. let me write this just last formula, I promise. So I have sort of standard diagonal instantons and standard diagonal negative instantons. And now from explicit data, and you can play this game in point of view 1, which is of course the simplest, but you can also play this game in the cubic matrix model, in the quartic matrix model, the example we've been looking more outside of that is the Yang-Lee example, but also the 2,5 minimal string, everything. So there's lots of things, and it looks as generic as possible. So if we focus on just, let's look at this main diagonal. As you see, the main diagonal, it's where, what I had in this blackboard before, there was a transmonomial that had an n minus m, and in the main diagonal, m is equal to m. So that transmonomial went away. So now this looks like a perturbative series, because there's no transmonomials. Yet this is very much non-perturbative, because all these sectors are not 0, 0 sectors. And so what you find is that this guy is equal to the following, as this structure. Let me rephrase, as this structure. So I said I was not going to write more formula, just structure. And of course, and as I said, this is pretty generic. This is an H. H, because this should remind you of the 't Hooft expansion, and the H would be for whole. But now it's sort of a whole of a brane and a negative brane. And so if you introduce the usual, our favorite parameter, but now with a GS, so there's an H there. There's an H there. So if I just introduce, it's an 't Hooft-like parameter, then this is equal to, okay, let me do it in orange, otherwise it looks like, this is equal to and so we see that we have obtained a new theory along the diagonal, which is a closed string theory along diagonal, where the train series parameters have been sort of upgraded to a modulus of that theory. Okay? This, by the way, this has been observed in the so-called Pont-Levé-1 gauge theory correspondence. But now what we're saying is that, well, first of all, it's explainable now, because it's, well, explainable, at least from a physical point of view. Of course, it was explained back in the past. It's explainable from a physical point of view, associated to these sort of, if you will, bound states of branes and negative branes, or of eigenvalues and anti-eigenvalues. But it's also saying that this story is completely generic, because this is basically true for any of those examples, of multi-critical examples, or any of those minimal string examples, any matrix model you want, they will all have this sort of feature. So let me see. What else can I say? And now we can also say, well, why this is open-closed duality. I can still write on this blackboard so that I don't. So this construction of these FGs, if you will, were obtained, these calculations that were done here were all done, if you want, starting from the matrix model side. I'm solving a string equation, and the string equation is an object that comes up in the matrix model side. So this is sort of an open string calculation. Now I sort of used, sorry. No, okay, I can do it like that. So these guys have been produced via open string, but they match the calculation of FGs coming from the holomorphic anomaly equations. There's lots of general results that have been recently obtained by Marcus, which come from the closed string side. And those results can now be matched coming from the open string side. And not only the FGs, which is sort of almost to say the easy part can be checked, but also the fact that the alien calculus simplifies also matches against formulae that I'm not going to go into that Marcus has derived recently. So there's sort of open-closed duality here, which you can think of a slightly different way, because instead of being the usual boundary conformal field theory versus conformal field theory in the worldsheet, it's more of a target space analysis where I solve matrix model 3 equations versus I solve closed string holomorphic anomaly equations, and I am reproducing the same objects at the level of trans series and at the level of alien calculus. So let me jump that. Okay, let me also jump that. So let me just say, okay, maybe I won't jump that. Let me say the first thing first, the last thing first, and then if there's 5 minutes left, I'll say one thing before. So you could ask exactly how is this construction being achieved, because at the end of the day, we already knew about digraph alpha duality, so what are we exactly talking about? So let me consider, for example, the cubic matrix model. And let me write down or draw the phase diagram of the cubic matrix model in the large n limit at complex Etoff coupling. And it looks like this. There's two regions which we can call Stokes phases, and where the eigenvalue configuration is on a single cut, and then it's basically that picture which is here for the spectral curve, and then there is a pinching cycle where I can tunnel non-perturbative stuff to, and this would be sort of the setting where you have the standard digraph alpha duality. But that's not the whole story. There's more stuff in this phase diagram. Then you have another region here, which we can call the anti-Stokes phase, where basically eigenvalues sit under two cuts. And from the point of view of the trans series, what has happened is that I moved from a trans series that was dominated by the perturbative sector, and now I turned on sigma 1. Well, this is in diagonal framing. I don't have any. But anyways, I turned on one of the trans series parameters, so now I have instantons, or eigenvalues, or d-branes, that can jump around the cuts, and they create a new phase. But that's not the end of the story. And this story occurs out here, which we call the trivalent phase. Well, we call everybody cool. It's not our name. Where eigenvalues sit in a trivalent configuration. Do note that the number of branch points is always the same. We always have 4 branch points. And in this trivalent phase, we need to turn on both trans series parameters, and the asymptotic series that we're finding here is what's written here in purple. Okay, and I decided that I will kill this one as well, so that I end exactly on time and you don't complain that I went over time. Thanks very much.
So here you did write FG as a function
Yes.
in the matrix model, for example. How can you see mu as a choice of integration?
So we can think of mu basically as some sort of tunneling of fractionated eigenvalues in the trivalent phase. Because if you're in the green phase, eigenvalues can only jump in integer values. But if you're in the purple phase, you can sort of imagine that, a bit of an eigenvalue went through. And so the way that you can think of the turning on of mu from a physical point in the matrix model is instead of jumping around eigenvalues, which leads to theta functions that Marcus knows very well, now there's all the characteristics are turned on, using this fractionation of eigenvalues. So this would be the way that we would think about them. The integration contours were already used somehow here when I had to do the deformation of integration contours to construct my full trend series out of matrix integrals.
Are you saying that FG mu is the FG mu that you find in trivalent phase?
Yes. And now mu, which was a trend series parameter, has been upgraded to a period.
Right, but what is mu in the trivalent phase there?
So that's what I'm saying, is associated with, okay, then I have to write down the last one, which I did not. Okay, so the way that we can write down the diagonal,
Now he's going to write it.
sorry,
No.
the way diagonal free energy, and I'm just going to tell you the diagonal piece is basically given by, you get maybe I'm not going to write, I'm going to write the 4 branch point free energy, and you're going to consider, well, there's a regularization that we have to do here that you know very well because you've done it, but let me not. Okay, and so if you fill in if you want the entries of the 4 branch point or 2-cut free energy, if you will, with the soft coupling and now mu, this is reminiscent of this story that you know very well of how multi-instantons and multi-cuts relate to each other. But now you don't have to do it just with integer values, you do it with an arbitrary value, and you reproduce the full trend series.
Why is not this the 2-cut matrix model? I mean, if you compute it perturbatively, this would be a 2-cut matrix model, right?
Well, it's a little bit more than that because this is the 4 branch point. So basically, well, again, I didn't want. What you're going to get is basically the dual, what people usually call the dual partition function. So if you want, is a Fourier transform of the 2-cut matrix model, and that's what encodes. So if you want, the trivalent phase is a sum over a bunch of canonical 2-cut models. Some sort of grand canonical formulation. Is this clear?
Well, sort of.
Yes.
I have a question about the diagram. So this also corresponds to the wall of marginal stability in Argyris Douglas.
Yes, sure. Then, of course, that's the other thing that you could say, and I already deleted them, is that then, very likely for Argyris Douglas series, you can also write down spectral curves the same way that you write down the minimal string spectral curve in terms of the multicritical one. Then, for specific, for a large class of Argyris Douglas series, you're able to do the same, which means that you can write down string equations for the Stokes phases of those series, and then bring them out into their trivalent phases and make predictions for the strong coupling of the series. So,
the question was rather, so in that case, the origin purple regions would correspond to regions in the modular space where there is only 2 BPS objects stable, and the green ones would correspond to regions where there is 3 BPS objects stable.
I think so.
Yeah, do you see this there somehow? Or?
No, this is the part that's still ongoing. As I said, part of this is still ongoing, so any comments that you have will be good. So it seems that we can construct string equations for these Argyris Douglas series. Much more than that is still less clear. What exactly can be computed or not. But if you have any input, I would appreciate it.
So we have recently looked at this using a tractor flow, and it's really, so as you see, the green regions have
Yes.
3 boundary points.
Okay, that we have not done.
Okay.
But we can talk.
They admit 3 stable objects, and the orange and purple regions only have 2 boundary
Okay,
points.
okay. Great. So we can talk about it. Yes.
So the 2-parameter trans series has a kind of A-type affine root system. Is there something known about other affine?
Well, at least the ones that relate to these Argyris Douglas series and Zagobin theories that are in this with these catastrophe polynomials, they will be A-type. So the other ones, I'm not even sure if they could be described by a one-matrix model. So I guess I don't know.
More questions? So let's thank Ricardo again.
Thank you very much.